Hello there, and welcome to the Late Mysteries channel. Tonight, we'll be drifting through the quiet science of space-time. This invisible fabric wraps around you, curves beneath you, and flows through every moment of your existence. You cannot see it or touch it, yet it holds everything together in a gentle, unbreakable embrace. Space-time is not empty nothingness. It is the stage upon which everything happens, the canvas where matter paints its slow dance across billions of years. Right now, as you rest, space-time curves ever so slightly around your body. The earth beneath you creates a soft dimple in this cosmic fabric, and you settle into it like a leaf floating on still water. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. But for now, just breathe. Let your eyes grow heavy and allow your mind to relax. Feel the gentle pull of gravity, which is nothing more than space-time itself, cradling you. Tonight, we'll explore how this mysterious fabric shapes reality in ways both vast and intimate, always working in silence, always holding you safe. Let's begin. Space-time curves around you right now, in this very moment. You cannot feel it, yet it shapes every second of your existence. Imagine the universe as a vast, invisible fabric stretched out in all directions, and upon this fabric rests everything you have ever known. Stars, planets, even your own body pressing gently into your bed. All of them create small dimples and curves in this cosmic weave. The heavier something is, the deeper it sinks into space-time. Earth is massive enough to create a noticeable curve, a gentle valley in the fabric that extends outward in all directions. You rest at the bottom of this valley, held in place by the shape of space itself. This is what we call gravity, though it feels more like falling than being pulled. You are always falling toward the center of Earth, but the ground rises up to meet you, and so you stay still. Right now, space-time bends around your body too. The curve is incredibly small, far too subtle for anyone to measure, but it exists nonetheless. Every atom in your body pulls at the fabric just a little, creating tiny wells that overlap and blend with the larger curve of the planet beneath you. It is a quiet partnership between you and the cosmos, each influencing the other in ways too gentle to notice. This fabric is not separate from space and time. They are woven together so completely that you cannot have one without the other. When you move through space, you also move through time. When time passes, space shifts around you. Together, they form a single entity called space-time, and it flows like water around everything that exists. Einstein discovered this over a century ago, though people found it hard to believe at first. Space seems so empty, so still. How could it bend and flex like cloth? Yet, that is precisely what it does. Space-time is flexible, responsive, always adjusting to the presence of matter and energy. It curves around the suns, warps near black holes, and ripples when massive objects collide far away in the distant universe. You do not need to understand all the mathematics to sense the truth of it. Simply lie still and feel the weight of your body pressing down. That sensation, that gentle pull toward the earth, is space-time telling you which way to fall. It is not a force reaching out to grab you. It is the shape of reality itself, guiding you along the path of least resistance, the natural curve that matter creates just by being here. And space-time never grows tired. It does not need rest or repair. It simply is, bending and flowing in response to everything, holding the universe together in a quiet, eternal dance. As you drift towards sleep, know that you are cradled in something far older and vaster than you can imagine, something that will continue long after you wake. The fabric beneath you is patient, timeless, and infinitely soft. The fabric of space-time does not stop at walls or ceilings. It passes through your room, through your home, through every building and forest and ocean on Earth. There are no gaps in this fabric, no places where it simply ends. Space-time is everywhere at once, threading itself through matter as easily as light passes through glass. Right now, the space-time in your bedroom is essentially flat. Earth curves it downward just a little, creating that gentle valley we discussed. But on such a small scale, the fabric lies smooth and still. If you could see it, it would look like a calm lake on a windless day, barely disturbed by the presence of furniture or walls, or your own resting body. But even this flatness is remarkable. Space-time adapts to whatever fills it. Where there is matter, the fabric bends. Where there is empty space, it stretches out smooth and even. Your room contains mostly empty space, the vast distances between atoms, and through all of that emptiness, space-time flows unbroken and serene. Scientists once believed that space was filled with something called the ether, an invisible substance that carried light from place to place. They imagined it as a kind of cosmic jelly, filling every gap and corner. But experiments proved the ether did not exist. Space was not filled with anything tangible. Instead, space itself was the medium, the fabric that allowed light to travel, waves to ripple, and time to pass. This was a strange idea to accept. How could nothingness be something? How could empty space have properties and structure? Yet space-time does. It can stretch and compress. It can carry ripples like a drumhead struck in the distance. It responds to energy and mass, curving around them, guiding their motion through the universe. In your room, space-time remains mostly undisturbed because the objects around you are small. A bed, a lamp, a sleeping person, these things barely register on the cosmic scale. Their influence on space-time is measured in numbers so tiny they require many decimal places to write down. But the influence is there, a whisper of curvature, a faint suggestion that matter is present. And beyond your walls, space-time continues outward without pause. It extends through your town, across continents, out past the atmosphere and into the void between planets. There is no boundary where space-time ends and something else begins. It is all one continuous fabric, connected and whole, stretching from the smallest speck of dust to the most distant galaxy. As you breathe slowly, in and out, space-time remains perfectly still around you. It does not flutter with your breath or shift with your heartbeat. It simply holds you, invisible and unchanging, a silent witness to your existence. And in this moment, you are part of something impossibly vast, a single thread woven into the cosmic fabric that binds all things together. Time is not the same everywhere. It moves at different speeds depending on where you are and how fast you are moving. Right now, as you lie still, time flows just a little bit slower near your feet than it does near your head. The difference is so small that you will never notice it, but it is real, measurable, and always happening. This occurs because of gravity, or more precisely, because of the way space-time curves. Your feet are closer to the center of Earth than your head, which means they rest deeper in the valley that Earth creates in space-time. Down in that valley, time moves more slowly. Up at your head, where the curve is slightly less pronounced, time flows just a tiny bit faster. If you could measure this difference with a perfect clock, placing one at your feet and one at your head, you would find that the clock at your feet falls behind by a few billionths of a second every day. It is not broken. It is simply experiencing time at a different rate. Gravity does not pull on clocks or people. It changes the flow of time itself. This seems impossible at first. Time feels absolute, the same for everyone, ticking forward at a steady, unchanging pace. But Einstein showed us that time is flexible. It stretches and compresses depending on gravity and motion. Near massive objects, where space-time curves steeply, time slows down. Far from massive objects, where space-time lies flatter, time speeds up. Astronauts orbiting Earth experience this too. They are farther from the planet's center than people on the surface, which means they rest in a slightly shallower part of space-time's curve. time flows a little faster for them. But they are also moving very quickly, and motion slows time down in a different way. The two effects balance each other out almost perfectly, but not quite. When astronauts return to Earth after months in space, they have aged just a fraction of a second less than people who stayed on the ground. You do not need to travel to space to experience time dilation. It happens to you right now, every moment of your life. Your feet are aging more slowly than your head. Of course, the difference is so small that it will never matter. You will not wake up to find your toes younger than your brain. But the principle is there, quietly at work, a gentle reminder that time is not as simple as it seems. And this is true everywhere in the universe. Time near the sun's surface flows more slowly than time on Earth. Time at the edge of a black hole slows almost to a stop. Time in the vast emptiness between galaxies rushes forward faster than anywhere else. Space-time weaves these differences together seamlessly, allowing the universe to function despite the fact that every clock ticks at its own unique pace. As you drift closer to sleep, let this thought settle over you. Time is not your enemy. It does not chase you or rush you forward against your will. It simply flows at different speeds in different places, always shaped by the curvature of space-time. And tonight, as time passes slowly and gently around you, you have all the moments you need to rest. Gravity does not pull. This is one of the most beautiful truths about the universe, and one of the hardest to accept. You have felt gravity your entire life as a downward tug, a force holding you to the ground. But that sensation is an illusion created by the way space-time curves beneath you. When you drop something, it does not fall because Earth reaches out and grabs it. It falls because space-time is curved, and the straightest possible path through curved space-time leads downward toward the planet's center. The object is simply following the natural geometry of space, moving along the path of least resistance, the groove carved into the fabric by Earth's mass. Imagine placing a heavy ball on a stretched sheet. The sheet sags beneath the weight, creating a bowl-shaped depression. Now roll a marble near the ball. The marble curves toward the heavy object, spiraling inward along the slope. It is not being pulled by an invisible force. It is simply following the contours of the sheet, moving along the path that the curvature creates. This is exactly what happens with space-time, though in 4 dimensions instead of 2. Earth's mass curves space-time around it, and everything nearby follows that curve. You, the moon, satellites, in orbit, even light itself, all of them travel along paths shaped by space-time's geometry. Gravity is not a force acting across empty space. It is the shape of space itself. This idea changed everything when Einstein proposed it over a century ago. Before that, scientists believed gravity was a mysterious force that somehow reached through empty space, connecting objects without touching them. Newton's equations described how gravity worked, but they could not explain what gravity was, or how it traveled faster than light to affect distant objects instantly. Einstein's answer was simple and elegant. Gravity does not travel at all. It is already there, built into the structure of space-time itself. When the sun moves, space-time takes time to adjust, and that adjustment propagates outward at the speed of light. But the curvature itself exists everywhere simultaneously, a smooth, continuous field that fills the cosmos. You can test this truth yourself, though not with your eyes. Lie perfectly still and pay attention to the sensation of weight in your body. You feel pressed against the bed, as though something is pushing you down, but nothing is pushing. The bed is pushing up against you, preventing you from following space-time's curve toward the center of Earth. You are trying to fall, naturally and effortlessly, but the ground keeps getting in the way. If the bed vanished beneath you, you would finally travel along the path that space-time wants you to follow. You would accelerate downward, not because a force grabbed you, but because that is the straightest possible line through the curved space-time around Earth. You would feel weightless during the fall, free from all forces, moving exactly as nature intends. And this is true for everything. Planets orbit the suns because they are following straight lines through curved space-time. The moon circles Earth for the same reason. Even light bends around massive objects, not because gravity pulls on it, but because space-time itself is bent, and light always takes the straightest available path. Gravity is geometry made visible, the universe's way of guiding everything along the most natural routes through existence. Light travels through space-time at a speed that never changes. In empty space, far from any star or planet, light moves at exactly 186,000 miles per second. Near Earth, in the curved space-time close to our planet, light still travels at that same speed, even near a black hole, where space-time bends so steeply that nothing can escape. Light maintains its pace. This constancy is remarkable. Almost everything in the universe can speed up or slow down. You can walk faster or slower. A river can flow quickly or barely move. Even the expansion of the universe changes over time, but light never varies. It is always moving at exactly the same speed relative to space-time itself. This happens because light has no mass. It does not push against space-time or sink into it the way matter does. Instead, light skims along the surface of space-time, riding the fabric like a wave on water. It follows the curves and bends that matter creates, but it never slows down or speeds up. It simply flows forward, always at the same pace, tracing out the geometry of the universe. Einstein realized that this constancy had profound implications. If light always travels at the same speed, then time and space must be flexible to make that work. When you move very fast, time slows down for you and distances shrink, just enough to keep light's speed constant from your perspective. When you stand still, time flows normally and space stretches out around you, but light still moves at the same speed you would measure. This seems impossible. How can light move at the same speed for everyone, no matter how fast they are moving? But the universe makes it work by adjusting time and space themselves. Space-time is not a rigid stage. It bends and flexes to ensure that light's speed remains constant, the one unchanging reference point in a universe where almost everything else is relative. Even the color of light changes depending on motion and gravity, but its speed does not. When light climbs out of a deep gravitational well, it loses energy and shifts toward red. When light falls into a gravitational well, it gains energy and shifts toward blue. But through all of these changes, the speed remains exactly the same. Light simply adjusts its wavelength and frequency to compensate, keeping its velocity constant through space-time. You can see light right now if you open your eyes, though that would disturb your rest. Photons from your ceiling, your walls, any source of illumination in your room, all of them are traveling at that same universal speed, bouncing off surfaces and entering your eyes in a continuous stream. Each photon has been traveling since the moment it was created, and it will continue at the same pace until it is absorbed by something. The light from the suns took 8 minutes to reach Earth today, crossing 93 million miles of space at its steady, unchanging speed. The light from distant stars has been traveling for years, centuries, even millions of years before finally reaching your eyes. Yet every single photon, near or far, old or new, moves at exactly the same speed through space-time. This constancy gives the universe structure. It provides a framework that everything else must follow. Time can stretch or compress, space can curve or flatten, but light's speed remains fixed, a universal constant that connects every point in space-time to every other point. And as you rest here, surrounded by darkness or gentle light, photons continue their eternal journey, never tiring, never slowing, always moving forward at the speed the universe has chosen for them. Every moment of your life, you are moving through space-time, not just through space as you travel from place to place, but through time as well. These two motions are connected in a way that never changes. The faster you move through space, the slower you move through time. The slower you move through space, the faster you move through time. Right now, as you lie still, you are moving through time at what feels like the normal rate, 1 second per second, 1 hour per hour. But you are not moving through space very much at all, at least not relative to the bed beneath you. This means almost all of your motion through space-time is focused on moving forward through time. Imagine space-time as a vast landscape, and you are always traveling through it at a constant speed. This speed never changes, but you can choose how to distribute your motion between space and time. If you move quickly through space, some of your motion gets redirected away from time, causing time to pass more slowly for you. If you stay still in space, all of your motion goes into time, causing time to pass at its fastest rate. This is why astronauts age more slowly when they travel at high speeds. Their motion through space uses up some of their motion through space-time, leaving less available for motion through time. The difference is tiny, measured in fractions of a second over months in orbit, but it is real and measurable. Their clocks slow down, their bodies age more slowly, their experience of time shifts just enough to prove Einstein's theories correct. You experience this too, though on a scale far too small to notice. When you walk across a room, time slows down for you by an incredibly tiny amount. When you drive in a car, time slows down by a slightly larger but still imperceptible amount. Even Earth's rotation carries you through space at about 1,000 miles per hour, which causes your time to flow just a little bit slower than it would if Earth stood still. But you are never aware of these changes because everyone around you is moving at roughly the same speed. Your clocks tick in sync with theirs, your aging proceeds at the same rate, your experience of time matches theirs. It is only when you compare your motion to someone moving much faster or much slower that the differences become noticeable. Light moves through space so quickly that it does not move through time at all. From a photon's perspective, if it could have one, no time passes during its journey. A photon emitted from a distant star and absorbed by your eye experiences its entire journey as a single instant. It crosses billions of miles in what feels to it like no time at all, because all of its motion through space-time is devoted to motion through space. You are the opposite. Almost all of your motion through space-time is devoted to motion through time. You drift forward through the hours and days, barely moving through space at all when measured against the vastness of the universe. And this is a peaceful way to exist. You are not racing anywhere. You are simply floating forward through time, experiencing each moment as it arrives, allowing the future to unfold at its own gentle pace. As you settle deeper into rest, feel yourself moving through space-time. You are traveling forward through time right now, 1 second at a time, moving along the path that the universe has laid out for you. Space remains still around you, or nearly so, and time carries you gently onward. There is no rush, no need to move faster or slower. The pace is already perfect, determined by the geometry of space-time itself. Earth moves through space-time, and you move with it. You are not just resting on the planet's surface. You are embedded in its gravitational field, caught in the flow of curved space-time that surrounds this massive sphere of rock and metal. Earth carries you along like a leaf floating on a slow river, and you have no choice but to travel where the current leads. This current is not like water flowing past you. It is space-time itself, bent and shaped by Earth's mass, and it extends outward in all directions. The curvature is strongest at the surface, where you rest, and gradually weakens as you move farther away. But even thousands of miles above Earth, the curve remains, pulling satellites into orbit and guiding the moon in its monthly journey around the planet. You do not feel this current because you are always moving with it. Fish do not feel the water they swim through, and you do not feel the space-time you travel through. It is simply there, surrounding you, supporting you, defining the path you follow through the universe. When you walk, you push against this current just a little, altering your path through space-time. When you stand still, you drift along with it, following the curve that Earth creates. This is why falling feels so natural. When you jump, you briefly escape the surface and follow space-time's curve more directly. For those few moments, you are in free fall, moving along the straightest possible path through curved space-time. You feel weightless because no forces act on you. You are finally moving exactly as nature intends until the ground rises up to meet you and the sensation ends. Astronauts in orbit experience this sensation continuously. They are falling toward Earth just as you fall when you jump, but they are also moving sideways fast enough that they keep missing the planet. Earth's curve pulls them downward, but their forward motion carries them around the planet instead of into it. They fall endlessly, circling the globe again and again, always moving along the natural curve of space-time without ever hitting the ground. You can imagine this current extending beyond Earth too. The moon travels through the same curved space-time, following its own groove in the fabric. The sun's creates an even larger curve, and Earth follows that curve in its yearly orbit. Each object creates its own curvature, and all of these curves overlap and blend together, forming a complex tapestry of gravitational fields that guide everything in the solar system. But Earth's current is the one that matters most to you. It is the flow that keeps you grounded, the curve that defines which way is down, the gentle pressure that holds you safe against the surface. Without this current, you would drift away into space, untethered and lost. With it, you remain exactly where you belong, cradled in the planet's embrace. As you breathe slowly and deeply, feel the weight of your body pressing down. That weight is not a burden. It is evidence that you are part of something larger, a massive sphere of matter that curves space-time around itself and carries you through the cosmos. You are not separate from Earth. You are woven into its gravitational field, traveling through space-time together, moving as one continuous system. And Earth, in turn, is woven into the sun's gravitational field, and the sun's is woven into the Milky Way's field, and the Milky Way drifts through the even larger currents created by clusters of galaxies. Each level nested within the next, each current flowing within a larger current, all of them connected by the seamless fabric of space-time. You are part of this endless hierarchy, a single point in a universe held together by gentle curves and invisible flows. Tonight, let Earth carry you. Trust the current that holds you safe. You do not need to do anything except rest. Space-time will continue flowing around you. Earth will continue curving the fabric beneath you, and you will continue drifting forward through time, supported and protected by forces you cannot see, but that will never let you fall. Every massive object creates a curve in space-time. This is true for planets and stars, but it is also true for smaller things. Your body creates a tiny curve. A grain of sand creates an even tinier curve. Even individual atoms bend space-time just a little, though the effect is far too small to measure with any instrument we possess. The amount of curvature depends on mass. More massive objects create deeper curves. The sun creates a deep well in space-time that extends across the entire solar system. Earth creates a smaller well that extends thousands of miles into space. Your body creates a well so shallow that it barely qualifies as a dimple, measurable only in theory, not in practice. But the principle is universal. Everything that has mass bends space-time. There are no exceptions. A mountain bends it more than a pebble. A pebble bends it more than a dust particle. A dust particle bends it more than a molecule. And on down through every scale of existence, each object contributing its tiny share to the total curvature of space-time. These curves overlap and combine in complex ways. Earth's curvature dominates the space around you, but your body adds its own small influence to the total. The bed beneath you adds its contribution too, as do the walls of your room and every object they contain. All of these curves blend together seamlessly, creating a smooth field of curvature that extends throughout the universe. This is how gravity works between objects. Earth curves space-time, and your body follows that curve. But your body also curves space-time, and Earth follows that curve too. The effect is mutual. You pull on Earth just as much as Earth pulls on you. The difference is that Earth is so much more massive that its motion in response to your pull is completely imperceptible. You fall toward Earth at a noticeable speed, but Earth falls toward you by an amount far too small to measure. Even light responds to these curves. When light passes near a massive object, it follows the curve that object creates in space-time. This bends the light's path, causing it to arc slightly rather than traveling in a perfectly straight line. During a solar eclipse, scientists can observe stars that appear slightly displaced from their true positions because their light has been bent by the sun's gravitational field on its way to Earth. Black holes create the deepest curves of all. Near a black hole, space-time bends so steeply that even light cannot escape. The curve becomes infinitely deep at the center, creating a point where space-time itself breaks down, and our equations can no longer describe what happens. But even black holes follow the same basic principle. They are simply objects with so much mass compressed into such a small space that their curves become extreme. You do not need to worry about black holes tonight. The curves around you are gentle and safe. Earth's curve is just deep enough to hold you against the surface, but not so deep that you cannot escape if you choose to. A powerful rocket can climb out of Earth's gravitational well and travel to other planets. You can jump and briefly escape the surface yourself, feeling the freedom of motion through space-time before the curve brings you back down. And in the vast spaces between stars, space-time lies nearly flat. The curves are spread so far apart that they barely overlap. Out there, an object could drift for millions of years without encountering any significant curvature at all. Space-time would stretch smooth and undisturbed around it, allowing it to travel in almost perfectly straight lines. But here, on Earth's surface, the curve is always present. You rest at the bottom of a gentle valley, surrounded by smaller curves created by everything nearby. The curvature is stable and predictable, shaped by objects that have existed for billions of years and will continue existing for billions more. You are safe in this curve, held in place by geometry itself, part of a system that has maintained its balance since long before you were born. Space-time existed before the universe had any matter in it. This is difficult to imagine, but it is what the mathematics tells us. In the earliest moments after the Big Bang, the universe was filled with pure energy. No atoms, no particles, no structures of any kind, just raw energy expanding outward into newly created space-time. The space-time itself was born at the same moment as the energy. Before the Big Bang, there was no space, no time, no fabric to curve or bend. Then, in an instant, space-time came into existence along with everything else. It did not expand into anything. There was nothing for it to expand into. Space-time itself defined what existence meant, creating the dimensions in which matter and energy could eventually form. For a fraction of a second, space-time was smooth and featureless. Energy filled it uniformly, with no clumps or variations to create curvature. Then tiny quantum fluctuations appeared, random variations in the density of energy from point to point. These fluctuations were incredibly small, but they were enough to begin the process of structure formation. As the universe expanded and cooled, energy began converting into matter. Particles formed from the cooling energy field, first quarks and electrons, then protons and neutrons, eventually atoms. These particles had mass and mass curves, space-time. For the first time, the fabric began to bend in response to what it contained. The early curvature was gentle and widespread. Matter was distributed almost uniformly throughout space, creating shallow curves everywhere, rather than deep wells in specific locations. But the tiny quantum fluctuations from earlier grew over time, amplified by gravity. Slightly denser regions attracted more matter, becoming even denser. Slightly less dense regions lost matter to their surroundings, becoming even emptier. Over millions of years, these variations grew into the structures we see today. Dense regions collapsed into galaxies and stars. Empty regions expanded into vast voids. The smooth space-time of the early universe became textured with curves of all sizes, from the shallow bends created by individual stars to the enormous curves created by galaxy clusters containing trillions of stars. But space-time itself never changed its fundamental nature. It remained the same fabric it always was, flexible and responsive, ready to curve around whatever matter happened to occupy it. The expansion of the universe stretched space-time outward, carrying galaxies apart from each other. But the local curvature around each galaxy remained stable, shaped by the mass contained within. Today, space-time continues to expand, though more slowly than in the early universe. Dark energy, a mysterious force we do not yet fully understand, drives this expansion, pushing space-time outward at an accelerating rate. But within galaxies, the expansion has stopped. The curvature created by matter is strong enough to hold galaxies together against the outward push of dark energy. You live in a small pocket of stability within an expanding universe. The space-time around Earth has not changed significantly for billions of years. The sun's curves, space-time, in the same way now as it did when the solar system first formed. Earth's curve has remained constant throughout all of recorded history. The fabric beneath you is ancient and stable, shaped by processes that began long before life appeared anywhere in the universe. And this fabric will continue long after you are gone. Space-time does not wear out or decay. It simply exists, responding to whatever occupies it, curving around matter and energy, carrying light and gravitational waves across the cosmos. It is the most fundamental thing in the universe, the stage upon which everything else performs, and it will endure until the universe itself ends, if it ever does. The curvature of space-time guides planets in their endless orbits around the suns. This happens without any force pulling on them, without any strings connecting them to the suns, without anything reaching across the empty space between. The planets simply follow the natural curves that the sun's mass creates in the fabric of space-time. Earth travels around the suns once every year, tracing an elliptical path through space. But from Earth's perspective, it is moving in a straight line. Space-time is curved around the suns, and Earth follows the straightest possible path through that curved space-time. It never deviates from its course, because the curve is always there, unchanging, guiding Earth along the same path it has followed for billions of years. The sun's mass creates a deep well in space-time, and Earth orbits near the edge of that well. It moves fast enough that it does not fall directly toward the suns, but not so fast that it escapes the curve entirely. It balances perfectly between these extremes, circling endlessly at just the right speed to maintain its orbit. Every planet in the solar system does the same thing. Mercury orbits close to the suns, moving quickly through the steepest part of the curve. Neptune orbits far from the suns, moving slowly through the shallow outer regions of the curve. Each planet has found its own balance point, its own stable path through the sun's gravitational field. Moons orbit planets in exactly the same way. Earth's moon circles our planet because Earth curves space-time around itself, creating a smaller well within the sun's larger well. The moon follows the curve that Earth creates, moving in a nearly circular path that carries it around our planet once every month. It has been following this path for billions of years, and it will continue for billions more. This system is stable because the orbits are nearly circular. A planet in a circular orbit experiences the same curvature at every point along its path. It never speeds up or slows down, never gets closer to or farther from the suns. It simply continues forever, moving through space-time at a constant speed, guided by geometry that never changes. Elliptical orbits are slightly more complex. Planets move faster when they are closer to the suns and slower when they are farther away. This happens because the curvature changes along their path. When a planet dives deeper into the sun's gravitational well, space-time curves more steeply and the planet accelerates. When it climbs back out toward the shallow regions, it slows down again. But even these changes are predictable, governed by the unchanging geometry of space-time. Comets follow even more elliptical orbits, sometimes diving close to the suns, and then swinging far out into the distant solar system before returning. They spend most of their time in the shallow outer regions where space-time curves gently, but once per orbit, they plunge into the steep inner regions, racing past the suns at tremendous speeds before escaping back into the outer darkness. All of these motions are silent and smooth. There is no friction in empty space, no resistance to slow the planets down. They could orbit forever if nothing disturbed them, and they will, for billions of years, until the sun eventually exhausts its fuel and expands into a red giant, disrupting the stable geometry that has held the solar system together for so long. But that will not happen for a very long time. Tonight, the planets continue their ancient dance, each following its own path through curved space-time. Earth carries you along as it orbits, moving at about 67,000 miles per hour around the suns. You do not feel this motion because space-time carries you smoothly along without any bumps or jolts. You simply rest, unaware of the vast cosmic machinery that holds you in your place. Space-time can ripple like the surface of a pond. When massive objects accelerate or collide, they create waves that travel outward through the fabric at the speed of light. These gravitational waves are incredibly subtle, stretching and squeezing space-time by amounts smaller than an atomic nucleus, but they carry information across the entire universe. Imagine two black holes orbiting each other, spiraling closer together over millions of years. As they circle, they disturb the space-time around them, sending out ripples in all directions. The ripples travel outward like rings, expanding from a stone dropped in water, though these rings move through four-dimensional space-time rather than across a two-dimensional surface. Eventually, after circling for eons, the black holes collide and merge into a single, larger black hole. This collision releases an enormous amount of energy, not as light or heat, but as pure gravitational waves. For a brief moment, those waves carry more power than all the stars in the visible universe combined, but the power is spread across the vastness of space. So by the time the waves reach Earth, they are almost imperceptibly weak. Scientists can detect these waves using instruments called interferometers. These devices measure changes in distance so small that it takes lasers bouncing back and forth over several miles just to notice them. When a gravitational wave passes through Earth, it stretches space-time in one direction and squeezes it in another. Everything stretches and squeezes together, the entire planet, the continents, even your body, though the effect is far too small to feel. The first gravitational waves ever detected came from two black holes that collided over 1 billion years ago. The waves traveled through space for all that time, crossing unimaginable distances, before finally reaching Earth in 2015. In that moment, space-time itself rang like a bell, and humanity heard the sound for the first time. These waves pass through everything without being blocked or absorbed. They travel through planets, stars, even through the hearts of galaxies. Nothing can stop them or slow them down. They simply move forward at the speed of light, carrying their message across the cosmos until the universe itself expands them into nothingness. Right now, countless gravitational waves are passing through you. Most come from events so distant or so weak that they create ripples too small to detect. Others might be strong enough to measure if we had instruments sensitive enough, and we happen to be looking in the right direction, but you will never feel them. The stretching and squeezing happens on a scale far below human perception. These ripples are a form of communication between distant parts of the universe. When a massive object moves, space-time adjusts, and that adjustment propagates outward, informing the rest of the universe that something has changed. In this way, gravitational waves connect every part of space-time to every other part, carrying information that would otherwise remain hidden. Binary star systems create gentle, regular waves as the stars orbit each other. Neutron stars spiraling together create waves that increase in frequency as the stars approach. Supernova explosions create brief, chaotic ripples as the dying star's core collapses. Even the Big Bang itself might have created gravitational waves, though these would be so ancient and stretched by cosmic expansion that we may never detect them. The universe is filled with these invisible ripples, overlapping and interfering with each other, creating a complex tapestry of disturbances in spacetime. Most are too weak to matter, but they exist nonetheless, a constant reminder that spacetime is not rigid or static. It is alive in a sense, responsive to everything that happens within it, carrying news of distant events across the vast emptiness between stars. As you rest, gravitational waves from colliding black holes, billions of light years away, pass through your body without disturbing your sleep. They stretch you by less than the width of an atomic nucleus and then release you, leaving no trace of their passage. You are transparent to these cosmic messengers, and they flow through you like ghosts, silent witnesses to the fact that space-time itself can move. Astronauts aboard the International Space Station age more slowly than people on Earth's surface. The difference is incredibly small, measured in tiny fractions of a second over months in orbit, but it is real and measurable. When astronauts return home after half a year in space, they are about 7 milliseconds younger than they would have been if they had stayed on the ground. This happens because of two effects working against each other. First, the astronauts are moving very fast, orbiting Earth at about 17,000 miles per hour. This speed causes time to slow down for them, according to special relativity. The faster you move through space, the slower you move through time, and at orbital speeds, this effect becomes just barely measurable. Second, the astronauts are farther from Earth's center than people on the surface. They orbit about 250 miles above the ground, where space-time curves less steeply than it does at sea level. In this shallower curve, time flows faster according to general relativity. The weaker the gravitational field, the faster time passes. These two effects work in opposite directions. The speed of the orbit slows time down, while the weaker gravity speeds time up, but the speed effect wins by a small margin. The time dilation from motion is slightly stronger than the time dilation from gravity, so the astronauts age more slowly overall. If you could watch an astronaut's clock from Earth, comparing it to your own, you would see their clock falling behind by about 28 microseconds every day. That is 28 millionths of a second, an amount so small that no human could ever perceive it directly. But atomic clocks can measure it easily, and when astronauts return to Earth carrying clocks that traveled with them, the clocks have fallen behind by exactly the amount Einstein's equations predict. This is not science fiction or theoretical speculation. It is a proven fact, demonstrated repeatedly over decades of space travel. Time genuinely flows at different rates depending on motion and gravity. An astronaut in orbit experiences fewer seconds than someone on the ground during the same period of Earth's rotation. Their hearts beat fewer times, their cells divide fewer times, their bodies age less. The effect becomes more pronounced the faster you travel or the farther you go from massive objects. Astronauts traveling to the moon experience slightly more time dilation than those in low Earth orbit because they traveled faster during parts of their journey. If someone could travel at a significant fraction of light speed, say half the speed of light, time would slow down for them dramatically. They might age only a few years, while decades passed on Earth. But no human has ever traveled anywhere near that fast. The fastest spacecraft we have built move at tiny fractions of light speed, creating time dilation effects measured in milliseconds or microseconds. For all practical purposes, time flows at nearly the same rate everywhere humans have ever been. The differences are real, but negligible for daily life. Still, the fact remains that time is not absolute. it does not tick forward at the same rate for everyone. Two people can experience different amounts of time passing, and when they reunite, one will be younger than the other. This seems to violate common sense, yet it is how the universe actually works. Time is flexible, shaped by motion and gravity, different for every observer depending on their path through space-time. As you lie still tonight, you age at the rate appropriate for someone resting on Earth's surface. An astronaut floating in orbit ages slightly slower. A photon of light racing across the universe does not age at all. Each travels through space-time at their own pace, experiencing time in their own way, all equally valid, all part of the same flexible fabric that Einstein revealed to us over a century ago. And tomorrow, when you wake, you will have aged by exactly the right amount, not too fast, not too slow, but at the pace determined by your position in Earth's gravitational field and your motion through space-time. Time will have carried you forward through the night at its gentle, inevitable rate, and you will continue your journey through the days and years ahead, moving through space-time 1 second at a time. Near a black hole, space-time curves more steeply than anywhere else in the universe. The fabric bends so sharply that it creates a point of no return, a boundary called the event horizon. Anything that crosses this boundary, whether matter, energy, or light itself, can never escape. The curve has become too steep to climb back out, but space-time itself never breaks. Even at the edge of a black hole, where gravity is stronger than anywhere else imaginable, the fabric remains continuous and smooth. It simply curves downward into an infinitely deep well, a funnel that narrows without limit toward the center. The mathematics suggests that at the very center lies a singularity, a point where space-time's curvature becomes infinite, and our equations can no longer describe what happens. Outside the event horizon, space-time is curved but still navigable. A spacecraft could orbit a black hole, just as planets orbit the suns, though the orbit would need to be much faster to avoid falling in. Light can escape from just outside the horizon, though it gets bent into strange paths as it climbs out of the gravitational well. Time flows much more slowly near the event horizon than it does far away, stretched by the extreme curvature. If you could watch someone falling toward a black hole from a safe distance, you would see their time slow down dramatically as they approached the horizon. Their movements would become sluggish, their clock would tick more and more slowly, and eventually they would seem to freeze in place just at the edge of crossing. From your perspective, they would never quite reach the horizon, their image growing dimmer and redder as the light struggled to escape. But from the falling person's perspective, nothing unusual happens. They cross the event horizon in a finite amount of their own time, probably without even noticing the moment they pass the point of no return. Time flows normally for them because they are in free fall, moving along the natural curve of space-time. Only when they look back at the universe they left behind would they see strange effects, watching the entire future of the cosmos unfold in fast motion as they fall. Inside the event horizon, space-time is so warped that all paths lead toward the center. There is no direction you could point that leads outward. Every possible direction in space points downward toward the singularity. You could fire your rocket engines at maximum power, trying to climb back out, but you would only succeed in reaching the center, slightly slower than if you did nothing. The curve is too steep to escape, and space-time offers no paths leading outward. This extreme curvature creates tidal forces that would tear apart anything falling in. The gravitational pull is so much stronger at your feet than at your head that the difference would stretch you like taffy. For large black holes, the ones at the centers of galaxies, you might survive crossing the event horizon and live for a while inside. But for smaller black holes, the tidal forces would destroy you before you reach the horizon. Still, space-time remains intact throughout all of this. It does not tear or break, even under these extreme conditions. It simply curves more and more steeply, following the geometry dictated by Einstein's equations. The black hole is not a hole in space-time. despite its name. It is a region where space-time curves so extremely that it creates effects unlike anything else in nature. Black holes are not rare. Nearly every large galaxy contains a supermassive black hole at its center, millions or billions of times more massive than the sun's. Smaller black holes form when massive stars collapse at the end of their lives. Thousands of these stellar mass black holes drift through our galaxy, invisible, except when they happen to pass near other objects. But you do not need to worry about black holes tonight. The nearest one is thousands of light years away, far too distant to affect Earth in any way. The space-time around you remains gentle and safe, curved just enough to hold you against the planet's surface. The extreme warping near black holes is fascinating to contemplate, but it exists in distant regions of space where humans will probably never travel. As you drift towards sleep, imagine the vast range of curvature that space-time can possess, from the nearly flat fabric between galaxies to the extreme curves near black holes. Space-time adapts to whatever mass it contains. Here, on Earth, you rest in a comfortable middle ground where space-time curves enough to matter, but not enough to pose any danger. The fabric holds you gently, stable, and predictable, shaped by forces that have maintained their balance for billions of years. The universe's space-time is expanding, carrying galaxies apart from each other. This expansion does not mean galaxies are moving through space. It means space itself is growing, stretching, like a balloon being inflated. Galaxies sit relatively still within space-time, but the space-time between them increases, creating more distance where there was less before. This expansion happens everywhere at once. Every region of space grows larger at the same rate. A stretch of space, 1 million light years across, grows by a certain amount each year. A stretch of space 2 million light years across grows by twice as much in the same time. The farther apart two galaxies are, the faster they appear to move away from each other, simply because more expanding space lies between them. The expansion is quite slow on human scales. In the space between Earth and the Moon, the expansion of the universe adds about 1/1,000,000th of a millimeter per year. This is far too small to measure and far too weak to overcome the gravitational forces holding Earth and Moon together. On the scale of galaxies, though, the expansion becomes significant. Distant galaxies move away from us at thousands or millions of miles per hour, carried by the expansion of space-time itself. Scientists discovered this expansion less than a century ago by observing that light from distant galaxies is shifted toward red wavelengths. This redshift happens because the light stretches along with space-time as it travels. A photon emitted billions of years ago has had its wavelength stretched by the expansion of the universe during its journey. By measuring how much the light has stretched, astronomers can determine how far away the galaxy is and how fast space-time is expanding. The expansion has not always proceeded at the same rate. In the earliest moments, after the Big Bang, space-time expanded incredibly fast, much faster than the speed of light. This rapid expansion, called inflation, stretched the universe from smaller than an atom to larger than a galaxy in less than a billionth of a second. Then inflation ended, and the expansion slowed to a more sedate pace. For billions of years, the expansion continued slowing down as gravity tried to pull everything back together. Scientists expected this trend to continue, possibly even reversing eventually, causing the universe to collapse back in on itself. But observations made in the late 1990s revealed something unexpected. The expansion is actually speeding up again, accelerating rather than slowing down. This acceleration is driven by something called dark energy, a mysterious property of space-time itself. We do not know what dark energy is or why it exists, but it acts like a pressure pushing space-time outward. As the universe expands and matter spreads out, becoming less dense, dark energy becomes more influential. Eventually, it will dominate completely, and the universe will expand faster and faster forever. But this happens on timescales of billions of years. Today, the expansion is fast enough to carry distant galaxies away, but slow enough that nearby structures remain stable. Our galaxy, the Milky Way, is gravitationally bound to our local group of galaxies. The space-time within this group is not expanding because gravity holds us together more strongly than dark energy pushes us apart. In the distant future, the accelerating expansion will carry most galaxies so far away that their light can never reach us. The universe will appear emptier and darker, with only our local group of galaxies visible against an increasingly vast void. Eventually, even our local group might be torn apart by the expansion, leaving each galaxy alone in an immense ocean of space-time. But these changes occur over trillions of years. Tonight, the universe is still filled with galaxies, and the expansion is gentle enough that it poses no threat to anything in our cosmic neighborhood. Earth orbits the suns at the same distance it always has. The moon circles Earth on its unchanging path. Gravity holds these systems together far more strongly than dark energy tries to pull them apart. As you rest beneath the stars, space-time continues its slow expansion all around you. The fabric grows imperceptibly larger, adding new space between galaxies, carrying them apart at speeds determined by their distance. This has been happening for 13.8 billion years, ever since the Big Bang created space-time and set it expanding, and it will continue for billions or trillions of years more until the universe reaches whatever fate awaits it in the unimaginably distant future. Space-time has no center and no edge. It simply exists, continuous and complete, extending as far as it needs to contain everything. You might imagine the universe as a sphere with Earth somewhere inside it, but this picture is misleading. There is no privileged location that can be called the center, no boundary where space ends and something else begins. When the Big Bang happened, it did not occur at a single point in space. It happened everywhere at once. Every location in the universe was part of the Big Bang because space-time itself was compressed into an infinitely small state. When space-time began expanding, every point moved away from every other point. There was no central explosion site, no origin point from which everything flew outward. This means you are at the center of the observable universe, and so is everyone else. Look in any direction, and you will see galaxies extending outward to the limits of observation, about 46 billion light-years away. But someone in a distant galaxy sees the same thing from their perspective. They are surrounded by galaxies extending equally far in all directions. Every location appears to be the center because there is no actual center. The observable universe has an edge only because light takes time to travel. You cannot see farther than light has had time to travel since the Big Bang. Beyond that distance, there might be more galaxies, more space-time, more of everything we can see nearby. We simply cannot observe it because not enough time has passed for light from those distant regions to reach us. The edge of the observable universe is not an edge of space-time itself, just an edge of what we can see from here. Space-time might be infinite, extending forever in all directions, or it might curve back on itself in ways we cannot directly perceive, creating a finite but unbounded space, like the surface of a sphere. A sphere has no edge and no center on its surface. You can travel in any direction and never reach a boundary, or find a special central point. Space-time could work the same way in 3 dimensions, curving through 4-dimensional space in a way that makes it finite yet without boundaries. We do not know which possibility is correct. The universe appears very flat on large scales, which suggests it might be infinite. But our observations cover only a tiny fraction of the total universe, and we cannot be sure what lies beyond our horizon. The answer to whether space-time is infinite or finite remains one of the deepest mysteries in cosmology. What we do know is that space-time is extremely uniform on the largest scales. If you look at a region of space containing billions of galaxies, it looks statistically similar to any other region of the same size. Galaxies are distributed evenly, forming clusters and filaments in patterns that repeat at every location we can observe. This uniformity suggests that space-time extends far beyond what we can see, possibly infinitely far, with no special regions or unique locations. This uniformity is also evidence that the Big Bang happened everywhere simultaneously. If the Big Bang had occurred at a specific point, we would see a gradient in the universe, with matter denser in one direction than another. Instead, we see the same cosmic background radiation coming from all directions, cooled by the same amount of expansion, indicating that every part of the observable universe has the same history. You can think of space-time as a fabric without seams or edges, woven from pure geometry, continuous in all directions, for as far as existence extends. It supports galaxies and stars, curves around massive objects, expands gradually over time, but never ends or reaches a boundary. It is complete in itself, requiring nothing outside itself to exist or function. This is both humbling and comforting. You are not at the edge of creation, nor are you far from the center. You simply exist within space-time, at a location as valid as any other, surrounded by a universe that extends equally in all directions. There is no special place to be, no privileged perspective from which to view the cosmos. Every location is equivalent. Every observer sees a similar view. Every point in space-time is connected to every other point. As you settle into sleep, let go of the need to be anywhere in particular. You are exactly where you belong, embedded in space-time at coordinates that are unique to you, but no more important than anyone else's. The universe does not favor one location over another. It simply exists, vast and uniform, holding everything in its seamless fabric, without center, without edge, without any need for either. Your past, present, and future all exist within space-time. This is one of the strangest implications of Einstein's theories, and one that physicists still debate. If space-time is a four-dimensional fabric where time is just another dimension like space, then all moments in time exist simultaneously within that fabric. The past has not vanished. The future is not yet to be created. Everything that ever was or ever will be already exists somewhere in the structure of space-time. Imagine space-time as a loaf of bread. Each slice represents a moment in time, showing the state of the universe at that instant. Your birth is one slice. This moment of reading is another slice. And your last moment will be yet another slice, somewhere further along the loaf. All of these slices exist at once, stacked together to form the complete four-dimensional structure. From your perspective, time flows forward. You move through the slices one at a time, experiencing each moment as the present. The slices behind you feel like the past, and the slices ahead feel like the future. But from outside space-time, if such a perspective were possible, all the slices exist together. There is no objective present moment, no universal now, that sweeps through the universe, bringing moments into existence. This view is called the block universe, and it suggests that time does not flow. Instead, all of history exists as a static structure, and the sensation of time passing is something that happens to conscious observers like you. You have the experience of moving from past to future, but this movement is just the relationship between your consciousness and the four-dimensional structure you inhabit. If this is true, then everything that will happen to you has already happened in a sense. It exists in the future slices of space-time, waiting for your consciousness to experience it. You do not create the future by making choices. You simply travel through the structure that already exists, experiencing the moments that were always there. This seems to eliminate free will, but perhaps it does not. Your choices are part of the structure too, embedded in the fabric alongside everything else. You choose freely, and those choices shape which future slices you travel through. Even though all the slices exist simultaneously, the paradox is difficult to resolve, and philosophers have been wrestling with it since Einstein first proposed his theories. Not all physicists accept the block universe view. Some argue that the present moment is special, that the past exists in a different way than the future, that time genuinely flows rather than being a static dimension. The mathematics of relativity allows both interpretations, and we do not yet have evidence to definitively choose between them. What relativity does prove is that simultaneity is relative. Two events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different speed. There is no universal present that everyone agrees on. This suggests that time cannot be as simple as it appears, that our intuitive understanding of past, present, and future needs revision. Perhaps the truth is somewhere between these extremes. Maybe the past exists as a fixed structure, while the future remains open. Maybe consciousness plays a role in collapsing possibilities into actuality. Maybe time has properties we have not yet discovered that will resolve these paradoxes. The mystery remains unsolved, and space-time keeps its secrets. For tonight, you can rest without worrying about these deep questions. Whether the future already exists or is yet to be determined, you are here now, experiencing this moment, and that is enough. Your consciousness flows through time at its own pace, and whatever lies ahead will reveal itself when you arrive. There is no rush to reach the future, and no way to return to the past. You simply move forward, one moment at a time, experiencing the slices of space-time in the order they appear to you. As you drift towards sleep, let time carry you gently forward. Tomorrow will come when it comes, and yesterday is complete and unchanging behind you. The present moment is where you live, where you experience existence, where your consciousness touches the fabric of space-time. And this moment, right now, is perfect for rest. Space-time curves more gently around smaller objects. A mountain bends the fabric less than a planet. A building bends it less than a mountain. A human body creates a curve so subtle that it is impossible to measure directly. Yet the principle remains the same at every scale. Anything with mass curves, space-time, and the amount of curvature depends directly on how much mass is present. Your body has mass, so it creates a gravitational field. This field extends outward in all directions, growing weaker with distance, but never quite reaching zero. In theory, your gravitational influence extends throughout the entire universe, though at such enormous distances the effect becomes meaninglessly small. The moon feels a tiny pull from your body, far too small to affect its orbit, but technically present nonetheless. The gravitational attraction between two people standing near each other is real but imperceptible. Your bodies pull on each other with a force measured in millionths of a pound, far too weak to overcome friction or any other force acting on you. You would need incredibly sensitive instruments to detect the gravitational pull between human bodies, and even then, you would struggle to separate it from all the other forces present. But scale matters enormously. Earth is so much more massive than you that its gravitational field dominates everything nearby. Your personal gravity field exists, but it is overwhelmed by Earth's field, like a whisper drowned out by a thunderstorm. Only when we consider objects far from planets and stars does the gravity of smaller masses become significant. Asteroids orbiting each other demonstrate gravity at smaller scales. Two asteroids of similar size can orbit their common center of mass, held together by their mutual gravitational attraction. Neither creates a very deep curve in space-time, but they create enough curvature to affect each other, binding them into a slow dance through space. Even dust particles exert gravity on each other. In the early solar system, tiny grains of dust in orbit around the young suns gradually clumped together under their own weak gravity. These clumps grew larger, attracting more dust, eventually forming pebbles, then boulders, then asteroids, and finally planets. Gravity shaped the entire solar system, starting from the gentle curves created by microscopic particles. At the atomic scale, gravity becomes so weak that it is usually ignored. Atoms interact through electromagnetic forces. which are vastly stronger than gravity at small scales. The gravitational attraction between two hydrogen atoms is about 40 orders of magnitude weaker than the electromagnetic force between them. For all practical purposes, gravity does not exist at the atomic level, yet gravity is cumulative. Gather enough atoms together, and their individual gravitational fields add up to something significant. A mountain is just an enormous collection of atoms, each contributing its tiny curve to space-time. The total effect becomes noticeable, enough to create local variations in Earth's gravitational field that scientists can measure. This is why gravity dominates on cosmic scales, while other forces dominate at small scales. Electromagnetic forces can be positive or negative, attracting or repelling, so they tend to cancel out when you have large collections of matter. Gravity only attracts, never repels, so it grows stronger the more matter you gather together. A galaxy contains so much mass that gravity becomes the dominant force shaping its structure. Despite being the weakest fundamental force in nature, you rest at a scale where gravity is noticeable but not overwhelming. Earth's gravity holds you firmly against the surface, but you can easily move around, lift objects, jump into the air. You are not trapped by gravity the way you would be near a black hole, nor are you floating freely the way you would in deep space. You exist in a comfortable middle range, where gravity matters enough to give you stability, but not so much that it restricts your freedom, and your own gravity, gentle and immeasurable, extends outward from your body even now. It curves space-time by an infinitesimal amount, creating a tiny dimple in the fabric that will exist as long as your body has mass. This curve connects you to the gravitational fields of everything else in the universe, from the smallest pebble to the largest galaxy. You are woven into the cosmic fabric by geometry itself, part of the continuous curvature that defines spacetime wherever matter exists. The fabric of spacetime connects everything in the cosmos, not just physically, but geometrically. Every object creates a curve, and every curve extends outward without limit, growing weaker with distance, but never completely vanishing. In this way, everything in the universe influences everything else, though most influences are far too weak to notice. The Sun's gravitational field reaches beyond Pluto, beyond the edge of the solar system, out into interstellar space. At enormous distances, the field becomes incredibly weak, but it never quite reaches zero. Stars passing within a light year of the Sun's feel a tiny pull toward it, just as the Sun's feels a tiny pull toward them. These mutual attractions shape the slow dance of stars around the galaxy's center. Our galaxy, the Milky Way, creates a gravitational field that extends far beyond the visible stars. Dark matter, a mysterious substance we cannot see directly, surrounds the galaxy and contributes most of its mass. This dark matter curves space-time, and that curvature holds the galaxy together, preventing stars from flying apart as they orbit at high speeds. Beyond our galaxy lie countless others, each creating its own curve in space-time. These curves overlap and combine, creating a web of gravitational fields that connect every galaxy to every other. Galaxies cluster together in groups, bound by their mutual gravity. These clusters form even larger structures called superclusters, the largest gravitationally bound systems in the universe. Between these structures lie vast voids, regions where matter is sparse and spacetime curves only gently. But even in the voids, spacetime remains continuous. There are no gaps or discontinuities, no places where the fabric ends. A photon of light can travel from one side of the universe to the other, moving through continuous spacetime the entire way, never encountering a boundary or discontinuity. This continuity means that events in distant parts of the universe can eventually affect us, though the effects travel at the speed of light and take vast amounts of time to arrive. When a star explodes in a distant galaxy, gravitational waves spread out from the explosion, traveling through spacetime at light speed. Billions of years later, those waves might pass through Earth, causing our detectors to register a brief ripple in the fabric. Light connects the universe even more directly. Every time you look at the night sky, you see light that has traveled through space-time from distant sources. The photons entering your eyes left their source years, centuries, or millions of years ago, traveling through the continuous fabric that connects their origin to your location. In this way, you have direct physical contact with distant objects, mediated by light traveling through space-time. But the connection is deeper than just light and gravity. Space-time itself is a unified field that extends everywhere at once. You cannot separate the space-time around you from the space-time around a distant galaxy. It is all one continuous fabric, one unified structure that contains everything. When you rest on your bed, you rest within the same space-time that holds galaxies billions of light years away. This unity suggests that the universe is fundamentally interconnected in ways we are only beginning to understand. Quantum mechanics hints at even deeper connections, where particles that have interacted remain entangled across any distance, their properties correlated in ways that seem to transcend space-time itself. These mysteries continue to puzzle physicists, suggesting that our understanding of space-time may still be incomplete. For tonight, it is enough to know that you are part of something vast and unified. The space-time around you connects to the space-time around every star and planet. The atoms in your body were forged in ancient stars and scattered across space by supernova explosions. The matter that makes you is recycled stardust, billions of years old, temporarily arranged in the pattern called you. And when you eventually return to the cosmos, as all matter eventually does, your atoms will scatter and become part of something else. They might drift through space for millions of years before becoming part of a new star or planet, but they will always remain within space-time, always connected to everything else, always part of the continuous fabric that binds the universe together. Space-time remains stable despite constant motion through it. Planets orbit stars, stars orbit galaxies, galaxies move through the expanding universe, yet space-time adjusts seamlessly to all of this activity. The fabric never tears or breaks, never develops flaws or weaknesses. It simply responds to whatever moves through it, curving and flexing in perfect accordance with Einstein's equations. This stability is remarkable when you consider how much is happening. Earth rotates on its axis once every 24 hours, carrying you through space at about 1,000 miles per hour. Simultaneously, Earth orbits the suns at 67,000 miles per hour. The sun orbits the center of the Milky Way at about 500,000 miles per hour. The Milky Way moves toward the Andromeda galaxy at about 70 miles per second, and the entire local group of galaxies moves through the universe at hundreds of miles per second. Add all these motions together, and you are moving through space-time at tremendous speed, following a complex spiraling path that combines rotation, orbit, and cosmic drift. Yet, space-time accommodates all of this motion without difficulty. The fabric curves around you smoothly, guiding you along your path, never resisting or creating friction. You move through space-time as easily as a fish moves through water. This is possible because space-time has no preferred reference frame. There is no absolute rest or absolute motion. You can consider yourself at rest while the universe moves around you, or you can consider the universe at rest while you move through it. Both perspectives are equally valid. Space-time does not care which reference frame you choose. The laws of physics work the same regardless. The stability extends to smaller scales too. Your heart beats, your lungs expand and contract, your blood flows through your veins. All of this motion happens within space-time, without disturbing the fabric in any measurable way. Space-time is far too stiff to be affected by such small masses moving at such low speeds. It takes planetary masses moving at significant fractions of light speed to create detectable ripples. But space-time does respond to large-scale motion. When a neutron star spirals into a black hole, the rapidly moving mass creates gravitational waves that propagate outward through the fabric. These waves represent actual disturbances in space-time, regions where the curvature oscillates back and forth as the wave passes. Yet even these waves do not damage spacetime. They simply pass through, and spacetime returns to its equilibrium state once the wave has gone. The expansion of the universe represents motion on the largest scale imaginable. Every region of space is moving away from every other region, and the rate of separation increases with distance. Yet, this does not tear spacetime apart. The fabric simply stretches, accommodating the expansion without developing holes or discontinuities. Spacetime can stretch infinitely without losing its fundamental properties. This stability comes from the fact that spacetime is not made of anything. It is not composed of smaller parts that can be broken or separated. It is the fundamental structure of reality itself, the stage on which everything else exists. It cannot break because there is nothing more fundamental for it to break into. It can only curve and stretch according to the rules of geometry. You benefit from this stability every moment of your life. Spacetime holds the suns in place, keeps Earth in orbit, and maintains the consistent gravity that allows life to exist. Without spacetime stability, the universe would be chaotic and unpredictable. Gravity would fluctuate, orbits would become unstable, and nothing could persist for long. But spacetime is utterly reliable, following mathematical laws that never vary, responding to mass and energy in precisely predictable ways. As you drift towards sleep, trust in this stability. Spacetime will continue holding you safely against Earth's surface all through the night. The planet will continue orbiting the suns on its ancient path. The stars will continue their slow dance around the galaxy's center. Nothing will shift or change in any way that affects you. The fabric that supports everything is stable, eternal, and infinitely reliable. Even empty space contains the quiet structure of spacetime. This seems contradictory at first. How can emptiness have structure? But spacetime is not nothing. It is a something, a field that exists everywhere, even where matter and energy are absent. The vacuum of space is not empty in any absolute sense. It is filled with spacetime, and spacetime has properties. These properties include the ability to curve, to carry waves, to expand. Even in regions where no matter exists, spacetime remains present as a background field. Scientists call this the fabric or the metric, the fundamental structure that defines distances and durations. Without spacetime, the concept of position would have no meaning. There would be no here or there, no separation between objects, no stage for events to occur upon. Quantum mechanics adds even more structure to empty space. According to quantum field theory, the vacuum is not perfectly still. It seethes with virtual particles that pop into existence for brief moments before vanishing again. These particles are not real in the usual sense, but they affect how real particles behave. The vacuum has energy, called zero-point energy, that arises from these quantum fluctuations. This vacuum energy might be related to dark energy, the mysterious force driving the universe's accelerating expansion. If spacetime itself possesses energy, then that energy creates a pressure that pushes spacetime outward. This pressure would be constant throughout the universe, the same in empty space as in regions filled with matter. Over cosmic timescales, this pressure could drive the observed acceleration, but these are deep mysteries that physicists are still working to understand. What matters for tonight is simpler. Spacetime exists even when nothing else does. It provides the structure that makes the universe possible. Without spacetime, there could be no motion, no separation, no time passing. Reality itself depends on this invisible fabric. The emptiest regions of space, far from any galaxy, still contain spacetime. Light can travel through these voids because spacetime is there to carry it. Gravitational waves can propagate through emptiness because they are waves in spacetime itself. The expansion of the universe stretches empty space just as it stretches space containing matter. Spacetime is everywhere, omnipresent, the most fundamental aspect of physical reality. When scientists talk about the shape or topology of the universe, they are talking about properties of spacetime itself. Is spacetime flat or curved on the largest scales? Does it loop back on itself or extend infinitely? These questions ask about the geometry of the vacuum, the structure present even in emptiness. The answers to these questions will tell us about the ultimate nature of reality. Is spacetime eternal, or did it have a beginning? Will it exist forever, or will it eventually end? Can spacetime exist without anything in it, or does it require matter and energy to give it meaning? These are some of the deepest questions in physics, and we do not yet know the answers. But we know spacetime is real. We can measure its properties, observe its effects, and use it to make predictions about the universe. It curves around massive objects in precisely the way Einstein predicted. It carries gravitational waves at exactly the speed of light. It expands at a rate consistent with observations of distant galaxies. Every test we perform confirms that spacetime exists and behaves according to the laws of general relativity. You rest within this structure right now, supported by geometry, held in place by curvature, moving through time along the path that spacetime defines. The fabric beneath you is invisible and intangible, yet more real than almost anything else. It is the foundation of existence, the medium through which everything happens, the silent background that makes the universe possible. As you close your eyes and surrender to sleep, spacetime remains exactly as it was. It will not change or shift beneath you. It will continue curving around Earth, guiding the planet in its orbit, carrying light from distant stars. And in the morning, when you wake, spacetime will still be there, unchanged and unchanging, holding you safe in its invisible embrace. The structure of spacetime is eternal and patient. It existed long before you were born and will continue long after you are gone. Tonight, you rest within it for a few hours, a brief moment in cosmic time. Tomorrow, you will wake and continue your journey through the days and years ahead, always moving forward through spacetime, always held by gravity's gentle curve, always part of the infinite fabric that connects everything in the universe. Sleep well, and good night.